Hello, welcome in the 16th lecture of my course Convective Heat Transfer. Here in this lecture we will be discussing about thermal entrance region once again, but in this case we will be considering the pipe is having constant heat flux boundary condition. In our last lecture we have considered about constant wall temperature condition. Here we will be considering the pipe is receiving constant heat flux. So as I have mentioned that we will be discussing about thermal entrance region with uniform heat flux. So let me first show you that what outline we will be following in my lecture. So first we will be deriving the energy equation and boundary conditions, okay, in the form of non-dimensional numbers, okay, for uniform wall heat flux around a duct, okay. Then we will be reducing those energy equations into simplified form, okay, for thermally developing region, that means the entrance length, okay, along with the necessary boundary conditions which will be evolving from the constant heat flux boundary condition, okay. Then we will determine the Nusselt number for thermally developing but hydrodynamically fully developed forced convection inside a tube having constant applied heat flux. We will be finding out the Nusselt number. Okay. So let us go inside this. First I will be showing you schematically what situation we are going to study in this. So as I have mentioned, we will be having a tube. So this is a tube having center line this one, r coordinate is, radial coordinate is in this side, okay, and axial coordinate is in this side, okay. And here we are considering thermally fully developed profile. So that means hydrodynamically fully developed profile, that means this parabolic boundary condition, and there we are considering that in the tube we are giving constant heat flux. Let us say the fluid whatever is coming, that is having some uniform temperature Ti, okay. So with this, as we are having hydrodynamically fully developed flow, so our W profile will be nothing but a parabolic profile, and once we non-dimensionalize this W bar with respect to the average W, so we will be getting W is nothing but 2 into 1 minus r square, okay, where r is nothing but r bar by r naught, okay. Next let us see for the wall heat flux, which is a constant Q, we can write down Q is nothing but K del T del R bar at R bar equals to 0. So which is coming from the wall, okay, boundary of the duct or tube, okay. So next we will be using this boundary condition for getting the value for temperature non-dimensionalization. This already we have shown in several cases. So let us use that same thing, theta is equals to T minus Ti. Ti is the inflow temperature for the fluid which is constant, okay, and there divided by Q R naught by K. So Q R naught by K you can get from here. So Q R naught will be multiplied by K, so it will be transforming into del theta del R, okay. So if we take this type of non-dimensionalization for our temperature, then we can write down temperature in the form of theta in this fashion, okay. So T equals to Ti plus Q R naught by K into theta. Let us find out the derivatives of temperature with respect to R first, because we will be requiring del T del R bar over here. So del T del R bar becomes Q, now here Q is constant, okay, and Ti is also constant, so this term goes to 0. So Q R naught by K, that can be taken out, so this Q R naught by K I have taken out, and then we are having del theta del R into del R by del R bar, okay. So what we are finding out over here, del R by del R bar is actually 1 by R naught, so ultimately it becomes Q by K del theta del R, okay. So from there we get, from this and this we get del theta by del R at R equals to 1 is equals to 1, okay. Next if we try to find out the other derivatives, unlike this del T del R, we will be finding out del T del Z. So if we do so, it becomes Q by K del theta del Z, okay, because we have considered T is equals to Ti plus Q by k r naught into theta. So you will be finding out that it is becoming, and we have considered z is equals to z bar by r naught, okay, because it is thermally developing zone, so entrance length, so the axial distance will be of the similar order of the radius, okay. So we have seen that if we do the derivative with respect to z bar, so it will become q by k into del theta del z, okay. So this is del theta del z, and then once again we will be having del z by del z bar. So del z by del z bar gives 1 r naught, and r naught and here q r naught, that r naught will be cancelling out, and subsequently we will be getting q by k del theta del z, okay. So if we do second time derivative, we will be getting similarly q by k r naught into del square theta del z square, okay. And if we do second time derivative of t with respect to r bar, so then we are getting q by k r naught del square theta del r square. So all these derivatives of the temperature, let us put in the energy equation. So energy equation is like this. We have seen as it is thermally fully developed, so u component and v component of the convection is not coming, only the axial component w component is coming into picture. And in case of conduction, we are having the radial conduction and axial conduction. Azimuthal conduction we have not considered over here, okay. Azimuthal symmetry has been assumed. Okay, then let us see if we put all these non-dimensionalization, that means convert t to theta, z bar to z and r bar to r, then we get over here once again w can be converted to w bar can be converted to w by multiplying w bar average. Then we can find out that the equation actually simplifies to w bar average into w, q by k into del theta del z in the left hand side for convection, in the right hand side for conduction, alpha by k into q by r naught, okay. And then we are having the radial conduction, non-dimensionalized radial conduction plus axial conduction term, okay. Further simplification, cancellation of terms from both sides, we can get w average r naught in by alpha, which is nothing but k by rho Cp, okay, k by rho Cp. Alpha is over here once again. So we can get over here some non-dimensional number, which is nothing but actually peclet number. Peclet number if we define based on the diameter, so peclet number by 2 will be coming over here, okay. And as w is actually a parabolic velocity profile, so that can be written as 2 into 1 minus r square, okay. So ultimately we get very simplified equation like this: 1 minus r square del theta del z is equals to 1 by peclet number plus radial conduction plus axial conduction, okay. Let us also see the boundary condition. So obviously at the wall r equals to at the axis r equals to 0, our del theta del r will be 0. That means there will be no gradient of temperature across the axis in the radial direction, okay. So this gives us the symmetry boundary condition sort of, and then r equals to 1 is nothing but your wall boundary condition. So in the wall boundary condition we are having actually del theta del r is equals to 1, which is nothing but constant heat flux boundary condition, okay. We have chosen theta such that this boundary condition actually reduces to a simplified form, del theta del r is equals to 1, okay. And then for the axial directions, we are having z tends to minus infinity and z tends to infinity. That means z tends to minus infinity means it is far before the entry of the pipeline, and z tends to infinity means in the downstream of the pipeline. So in case of z tends to minus infinity, we will be having theta tends to 0, because it becomes Ti minus Ti divided by Ti minus Tw, so it becomes 0. And in case of z tends to infinity, though it is supplying heat via the heating coils as a function of constant heat flux, but temperature definitely will not be going to infinite, it will be always finite. So let us have theta is finite boundary condition at z tends to infinity, okay. So with this equation and boundary conditions, two boundary conditions of r and two boundary conditions of z, we can describe the thermally developing region inside a pipeline, okay, in which we have considered that hydrodynamically fully developed flow is going on, okay. Next let us try to see some scale analysis. So for the thermally developing zone, we need to see that what is first the scale of your axial direction and radial direction. As it is thermally developing zone, so the zone will be very small, obviously that will be of the order of R naught. Okay, so Z will be coming of the order of 1, because Z is nothing but Z bar by R naught. Okay, and in case of radial direction, 1 minus R is nothing but R naught minus of R bar, R naught minus of R bar divided by R bar. So that will be coming in the form of the boundary layer thickness delta naught. Okay, so this to scale, once we decide, then we can find out quickly the other scales. For example, from the boundary conditions, here you see del theta by del R needs to be of the order of 1. So as we have decided R is of the order of delta naught, so obviously theta needs to be of the order of delta naught. Okay, because this del theta by del R needs to be of order 1. Okay, so if R is of the order of delta naught, theta obviously needs to be the order of delta naught. Okay, so we have already found out Z, R and theta order. So let us find out the rest terms of the equation. So first let us start with 1 minus R square. So 1 minus R square will be 1 minus R plus 1 by R, 1 plus R. Okay, so here we can get it will be also of the order of delta. Why? Because 1 plus R is actually of the order of 1, because R is of the order of 1. Okay, so 1 plus 1, it will be of order of 2. So basically this 1 minus R square will be of the order of delta naught. Here this 1 minus R is actually determining what is the order. Okay. Next, let us see that what is the order of convection. So first in this equation we have the convection. So convection was W into del theta del Z. Okay, as we have seen that part of convection, this W is nothing but 2 into 1 minus R square. So 1 minus R square is of the order of delta naught. So this W can be written in the order of delta naught, and del theta by del Z, Z is of order 1 and theta is of order delta naught, just now we have said. So we get the convection is of the order of delta naught square. Okay. Then radial conduction, if you think about, so in this equation if you see, the radial conduction is having 1 by Peclet number and then theta's order and R order square. Okay, so here also R order square, theta's order over here. Okay, so we will be finding out radial conduction becomes 1 by Peclet number into delta by delta naught square. Okay, so radial conduction order we have found out. Let us see the axial conduction. In case of axial conduction, it is nothing but 1 by Peclet number, and then let us go back to the equation, 1 by Peclet number, then order of theta and order of Z. Order of Z is 1, that's whole square will be also of order of 1, and theta will be of order delta naught. So ultimately we get 1 by Peclet number into delta naught by 1. Okay. Now you see this order is actually smaller compared to this one. Okay, because delta is very small. Okay, so we can get the conduction order is actually this one, which is the radial conduction. Axial conduction can be neglected in compared to the radial conduction for small delta obviously. Okay, so what we can take, let us equate the convection order and radial conduction order. So delta naught square, which was the convection order, and 1 by Peclet number delta naught by delta naught square, which was the radial conduction order. If we equate, from here we can get delta naught is of the order of Peclet number to the power minus 1/3. Okay, so we have got the boundary layer thickness order. Okay, so it will be helping us to construct the similarity variable. So let us try to have similarity variable in case of our thermal entrance region. Okay, so here once again schematically I have shown the thermal entrance region. So up to this we will be having the thermal entrance region. So in that, as we have already taken Z is of the order of 1, and earlier we have taken 1 minus R is of the order of delta naught, and in the last slide, by equating the convection and conduction order, we have showed that delta naught is actually Peclet number to the power minus 1/3. So 1 minus r can be written as Peclet number to the power minus 1/3. Okay, and let us take the similarity variable eta in this fashion. Eta is nothing but Peclet number to the power 1/3 into 1 minus r. Okay, so r becomes 1 minus Peclet number to the power minus 1/3 into eta. So eta is our similarity variable. So if we take so, here I have clearly showed what is the variable eta. So if we take so, then quickly we can try to find out the derivatives of theta, which will be useful for finding out the derivatives of temperature, okay, theta. So let us find out first del eta del r. So del eta del r, simply it becomes minus Peclet number to the power 1/3, okay, and then subsequently if we try to find out del theta del r will be nothing but del theta del eta into del eta by del r. Del eta by del r just now we have found out as minus Peclet number to the power 1/3. So it becomes del theta by del r becomes minus Peclet number to the power 1/3 into del theta del eta. Okay. Then let us do once more derivative. If we do once more derivative, del square theta del r square, it becomes once again Peclet number to the power 1/3 into del square theta del eta square. We need to plug in this del eta del r once more over here from this del theta del r to del square theta del r square. Okay. So both the radial conduction parts we have obtained. Next, let us find out the value of 1 minus r square, which is there in the convection side due to the parabolic velocity profile. So it becomes actually 1 minus r into 1 plus r, which is nothing but Peclet number to the power 1/3 into eta multiplied by 2 minus Peclet number to the power minus 1/3 into eta. This 2 is nothing but 1 plus 1 minus Peclet number to the power minus 1/3 into eta, which is 1 plus r, and this is actually your 1 minus r. Okay. So after that, if we try to put everything in this equation, then we simply get Peclet number to the power minus 1/3 eta. Okay, so into 2 minus Peclet number to the power minus 1/3 into eta, this is nothing but your 1 minus r square we have derived over here, into del theta del z is equals to 1 by Peclet number, and then in the right hand side we have already evaluated del square theta del r square and del theta del r. Let us put those. So del square theta del r square is nothing but Peclet number to the power 2/3 into del square theta del eta square, and r we have written as here r we have written as 1 by 1 minus Peclet number to the power minus 1/3 into eta. Okay, and del theta del r is nothing but Peclet number to the power minus Peclet number to the power 1/3 into del theta by del eta. Okay, and last term remains as it is over here because z is of order 1. Okay. So if you simplify this equation little bit, then we get this type of equation, and we find out that in 3 terms here in axial conduction, in this del theta del eta term, and a part of this del theta del z term we are having Peclet number to the power minus power. Okay. Now for large Peclet number limit, okay, so taking Peclet number very large, what we can do, those terms we can cancel out and make our equation simplified. So in case of large Peclet number, we can drop down these terms and we can write down 2 eta del theta del z in the left hand side coming from the convection, and in the right hand side del square theta del eta square coming from the radial conduction only. So this becomes very simplified equation for large Peclet number cases. Okay. And let us see also the corresponding boundary conditions. So here first boundary condition we had earlier in terms of r, it was earlier at r equals to 1, which is at the wall, del theta by del r equals to 1, which was actually constant heat flux boundary condition. So from there first we need to convert to your eta boundary condition, because we have already seen that eta is equals to 1 minus r into Peclet number to the power 1/3. So here if we put the value of r equals to 1, then we get eta equals to 0. Okay, so at eta equals to 0, the boundary condition comes out to be, though theta will not be changing, but due to this r to eta, r to eta, one Peclet number to the power 1/3 will be coming out. So, the boundary condition will transform into Peclet number to the power 1/3 into del theta del eta is equals to 1. Okay. So, this becomes the equation and this is the boundary condition. Now, you see the boundary condition is Peclet number to the power 1/3 into del theta by del eta is equals to 1 is a complicated one. Let us try to replace theta by some simplified one, so that this boundary condition can be written in some better format. Okay. So, let us take theta equals to Peclet number to the power minus 1/3 into theta 1. This will not change the equation, because in equation both the sides we are having theta. So, this Peclet number to the power minus 1/3 can be cancelled from both the sides, but it will be definitely helping in this boundary condition, because in boundary condition we are having Peclet number to the power 1/3 into del theta by del eta equals to 1. So, once we put this theta 1 equals to theta by Peclet number to the power minus 1/3, those Peclet number to the power 1/3 and Peclet number to the power minus 1/3 from here will be cancelling out and it will become simplified. Okay. So, let me show you, after putting this theta equals to Peclet number to the power minus 1/3 into theta 1, what form of boundary condition we get. So, this is the equation. Now, you see theta has been converted to theta 1 and Peclet number to the power minus 1/3 has been cancelled from both sides. Okay. But boundary condition, it is very surprisingly changing to at eta equals to 0, which is nothing but r equals to 1, it is changing to very simplified form del theta 1 by del eta equals to minus 1. Earlier it was Peclet number to the power 1/3 into del theta del eta equals to minus 1. Okay. So, this simplified equation and boundary condition we get. Apart from that, we are having some other boundary conditions also. Let us see. So, first, that r tends to delta, theta tends to 0, or so this was the boundary condition earlier. So, from here we get, if eta, as eta tends to 0, theta 1 tends to 0. Okay. And at the inlet, as z tends to 0, theta tends to 0. Okay. So, this is being converted to, at z tends to 0, theta 1 tends to 0. So, now we have got theta 1's equation and 1, 2 and 3 boundary conditions for theta 1, 2 for eta direction and 1 for z direction. Okay. Let us now try to get the similarity variable once more in between eta and zeta. Eta and z. So, first let us try star quantities. Eta star is equals to e to the power alpha 1 into eta, z star is equals to e to the power alpha 2 into z, and theta 1 star is equals to e to the power alpha 3 into theta 1. Okay. And first we need to find out all these derivatives. We have to replace all these theta 1's to thetas in equation as well as boundary conditions. For that, let us put these star quantities in the equation first. So, here you can get in the left hand side, as we are having eta, theta 1 and z, we are getting e to the power alpha 2 minus alpha 1 minus alpha 3 in the convection side. In the conduction side, we are having delta square, it is a mistake over here, it will be delta square theta 1 by del eta square. So, it becomes actually del square theta 1 star by del eta square, and it releases e to the power 2 alpha 1 minus alpha 3. Okay. So, then the boundary condition, if you see the very important boundary condition, it becomes eta star equals to 0, it will be e to the power alpha 1 minus alpha 3 into del theta 1 star by del z star is equals to minus 1. Okay. Now, we are having this is the equation and this is the boundary condition. From here easily we can tell that okay, if we take alpha 1 equals to alpha 3, then this boundary condition becomes very simplified. Okay. And other boundary conditions at eta tends to infinity and z equals to 0 remains as usual similar, theta 1 star tends to 0 and theta 1 star equals to 0. Okay. So, one relationship between the constants alpha 1, alpha 2 and alpha 3 already we have obtained from the boundary condition alpha 1 equals to alpha 3. Now, let us see the equation coefficients. If you equate the power of the e to the power, if you equate the coefficients of this left hand side and right hand side terms and get a relationship between alphas, then you can write down from there alpha 2 minus alpha 1 minus alpha 3, which was the power of E in the convection side, equals to 2 alpha 1 minus alpha 3, which is the power of E in the conduction side. Okay. So, from here we can get if you further simplify, alpha 2 is equals to 2 alpha 1 minus alpha 1 equals to alpha 1. Here alpha 3 has been cancelled from both the sides. Okay. And if you further proceed, you get alpha 2 equals to 3 alpha 1. So, we have got two relationships, one is alpha 2 equals to 3 alpha 1 and another one is alpha 1 equals to alpha 3. Using this, let us try to eliminate alpha 2 and alpha 3 and write down these star equations in terms of alpha 1 only. So, we get eta star is equals to e to the power alpha 1 eta, z star is equals to e to the power 3 alpha 1 z, because alpha 2 is actually 3 alpha 1, and theta 1 star is equals to e to the power alpha 1 theta, because alpha 3 is equals to alpha 1. Okay. Now, if we put that from here, if we try to get the similarity parameter zeta, so these two equations will be helping me. So, let us see from these two equations we can get eta star by z star to the power 1/3 is actually equals to eta by z to the power 1/3. Okay. And from these two we can easily get that theta 1 star by z star to the power 1/3 is equals to theta 1 by z to the power 1/3. Okay. And this can be also written as we are seeing that the order is more or less same, it can be also written as this will be a function of eta by z to the power 1/3. So, ultimately let us have the similarity variable zeta actually equals to eta by z to the power 1/3 multiplied by a constant a, which needs to be determined. Okay. So, we have actually written the similarity variable side by side. Let us also take theta 1 is nothing but b into z to the power 1/3 f of zeta. Okay. So, it comes from here. Okay. So, b into z to the power 1/3 into f of zeta, where zeta is this one. Okay. So, after defining this zeta and theta 1 in form of zeta, let us first try to see what is the derivative of zeta with respect to eta and z. Okay, these are very simple. Make the derivative of this one with respect to eta first, considering z constant, and this you do by considering eta constant. Okay, once you do these two derivatives, you will be getting. Using these two, let us try to find out the values of temperature derivatives. So, first del theta 1 by del eta. So, if you do chain rule, then you will be finding out it is turning out to be a b f dashed. Okay, a b f dashed it will be turning out to be. Here we are using this del zeta del eta, which we have found out over here, and del theta 1 del zeta we will be making derivative of this one. So, b will be coming and a will be coming from here. As a result, it is a b f dashed. Okay. If we proceed further, second derivative of theta with respect to eta will become a square b z to the power 1/3 f double dashed. Okay. And if we find out what is the derivative of theta 1 with respect to z from its dependence of z over here, then we will be getting that it requires derivation of two multipliers. So, that if we do one by keeping one constant and doing the other derivative, and then keeping the second one constant doing the derivative of the first one, we get a simplified form like this. This is nothing but b by 3 into z to the power 2/3 into f minus zeta f dashed. So, we have obtained both the temperature derivatives of theta 1, okay, temperature derivatives of theta 1 with respect to eta and z respectively, second derivative and first derivative of z. These are there in the energy equation. So, let us try to put all these values in the energy equation. So, as I have told 2 eta, and this is nothing but your del theta 1 del z. Okay, so, del theta 1 del z. So, this term we have put over here, and in the right hand side we are having del square theta 1 del eta square, which is this one. Let us put it over here. Okay. Now, here you see in this equation we can see that b can be cancelled. So, ultimately you get equation having a square only. Okay. And you see little bit of modification of this eta by z to the power 1/3, which will be zeta. We can get a simplified form like this. Okay. if you change the sides of this one, then you will be getting f double dash plus 2 zeta by 3a cube into zeta f dash minus f is equals to 0. Okay. Now you see boundary conditions subsequently will be changing to at zeta equals to 0 a b f dashed, which is nothing but a b f dashed is nothing but del theta 1 del eta. So we have actually seen that here a b f dashed is nothing but del theta 1 by del eta, which is actually equals to minus 1. So a b f dashed is becoming minus 1. Okay. And obviously the other boundary condition, as zeta tends to infinity, f is becoming 0. Okay. So this is the equation, and we are having two boundary conditions over here. Okay. If we proceed further and try to find out what is the value of a to make this equation simplified in Luke. So we can choose the value of a in this fashion, 3a cube equals to 1. If we choose, then you see 3a cube equals to 1. If we choose, then the equation becomes very simple. Okay. So we can drop down this 3a cube. So in that case apart from this one, we can also take this a b equals to 1, then this boundary condition will be also very simple, at zeta equals to 0 f dash equals to minus 1. Okay. So we have got 3a cube equals to 1 and a b equals to 1. If we choose like this, then from here we can get individual values of a and b like this. A is 2 by 3 to the power 1/3 and b is 3 by 2 to the power 1/3. Okay. Now let us plug in all these things in our equation. Our similarity variable becomes eta by 3z by 2 to the power 1/3, and theta 1 becomes 3z by 2 to the power 1/3 f. Okay. So earlier here we had a and b respectively. Once we get the value of a and b, we can get the actual value of zeta and theta 1 over here. Okay. And in case of equation, the equation becomes now very simplified in Luke, as we have put 3a cube equals to 1, and the boundary condition also looks very simple, as we have put a b equals to 1. So this is my equation, and we will be having two boundary conditions in this fashion. Okay. Now for finding out f, this is not a very simple equation, as we are having second order, first order and 0th order. So it is we need some numerical simulation. Okay. So you have to find out f using numerical simulation. And if you try to get back the value of theta, as we have taken the equation over here, from theta 1 we can go back to theta, as we have taken theta is nothing but peclet number to the power 1 minus 1/3 into theta 1. So if you go back there, so theta becomes 3z by 2 peclet number to the power 1/3 into f. So once you get the value of f by numerical simulation of that, then you can get the temperature distribution, non-dimensional temperature distribution theta in this fashion. Okay. Next, let us try to get the value of Nusselt number. So in order to do so, first we will be coming the heat transfer coefficient H, which is nothing but Q by Tw minus Tb. Okay. So if you proceed further, so you will be getting that H R0 by K, which is which can be Nusselt number. 2 into H R0 by K is Nusselt number. So there you can find out this is nothing but your K R0 by K by Tw minus Tb, and Tw minus Tb can be written as Tw minus Ti minus of Tb minus Ti. So now this can be written as theta w, and this can be written as theta b, because Tw minus Ti by Q Rw by K is nothing but theta w, and Tb minus Ti by Q R0 by K is theta b. Okay. So we get H R0 by K is nothing but 1 by theta w minus theta b. Okay. Proceeding further, Nusselt number will be nothing but 2 into this factor. So this becomes 2 by theta w minus theta b. Okay. Now theta b, about theta b we know this will be nothing but w theta dr, integration from 0 to r, and then w dr from 0 to r. As it is thermally fully developed, so w will become actually 2 into 1 minus r square. So 2 can be cancelled from denominator and numerator, okay. And we see that theta w, okay, theta w as we have shown in the previous one, theta variable, so theta was 3z by 2 Peclet number to the power 1/3 and then f of zeta, okay. Now as we are at wall, so obviously zeta will be 0, so we get theta w is this fashion. So here you see we have got theta w, here we have got theta b which is 0, so we can easily find out the Nusselt number. So Nusselt number becomes, so theta w is nothing but this one, so this quantity we have written, minus theta b which is 0, so this is actually becoming 2 by theta w, okay. Now once you get what is the value of this f naught, okay, so after simulation of the equation and the boundary conditions we have shown governing equation, so then you will be getting the value comes out to be 1.639, okay. So Nusselt number becomes 1.639 by z by pe to the power 1/3. So here also you can see Nusselt number is a function of z and Peclet number over here, okay. So with this I end this lecture. Let us summarize what we have learned. So first we have seen the governing equation for thermally developing but hydrodynamically fully developed forced convection inside a tube having constant applied heat flux. So this is very important, constant heat flux. So the equation we have reduced to this form, 2 eta del theta del z is equals to del square theta del eta square, okay. Corresponding boundary conditions, so this is the boundary condition at the wall, okay, del theta del r equals to 1, and these are the boundary conditions at the axis, okay, and this is the boundary condition at the entry. Once we reduce to subsequent stages via the similarity variable and theta to theta 1, finally we get f double dash plus zeta into zeta f dash minus f is equals to 0, with the boundary condition f dash 0 is equals to minus 1 and f infinity equals to 0. We have also proceed further to show the relationship of Nusselt number with respect to Z. So Nusselt number for thermally developing but hydrodynamically fully developed forced convection inside a tube having constant applied heat flux comes out to be Nusselt number is equals to 1.639 Z by Peclet number to the power 1/3, okay, which is dependent on Z, okay. So this we have learnt in this lecture. So after this one, let us see that how far you have understood in this lecture. So let me test your understanding. We are having 3 questions as usual. So first one is, in thermally developing but hydrodynamically fully developed region inside a duct having constant heat flux, radial conduction is of the order. You have to give me the order of the radial conduction. 4 options are there. I think already you have understood which one is the correct answer. So options, let me tell you once again: 1 by Peclet number, 1 by Peclet number into 1 by delta square. Here we are having 1 by Peclet number into 1 by delta, and finally Peclet number. So obviously you have got the correct answer. The 1 by Peclet number is the correct order, okay. This we have discussed also in this lecture. Next one, in thermally developing region, Nusselt number depends on both Peclet number and Z for which case, okay. Though it is in this lecture we have discussed about constant heat flux, but let me ask you that your Nusselt number depends on both Peclet number and Z for which case? Constant wall temperature, constant heat flux. None of these cases will be giving you the dependence of Nusselt number and Peclet number and Z. And fourth option is both A and B are true. If you go to this lecture and see the previous lecture also, then probably you have understood correct one is both A and B. Actually in thermal entrance region, the Nusselt number will depend on both Peclet number and Z. So that's why it will not be depending on the whether wall heat constant temperature or constant heat flux, that will not be mattering. It will be mattering whether it is thermal entrance region or not, okay. So it will be having Z dependence as well as it will be having Peclet number dependence. Last question is like this: in thermally developing but hydrodynamically fully developed region inside a duct having constant heat flux, 1 minus r is of the order, this is very simple, 1 minus r obviously we have used for our similarity variable. So 1 minus r is of the order of 4 options we are having, peclet number to the power minus 1/3, peclet number to the power 1/3, peclet number and 1 by peclet number. Very simple, probably you have understood the correct answer. So correct answer is the first one, peclet number to the power minus 1/3. Okay. So with this I end this lecture. In the next lecture we will be discussing a special case which is called Rayleigh-Bénard convection, which we can observe in case of flow inside a duct, inside two parallel plates actually, okay, 3-dimensional parallel plates. There we will be understanding what type of convection cells are there, and we will be going for stability analysis of that one. Okay. If you have any query regarding this lecture and any other general query about convective heat transfer, please keep on posting in our discussion forum. Thank you.